Hello there, and welcome to the Sleepy Station. Close your eyes and let the darkness behind your eyelids become the infinite canvas of space itself, where we begin our journey at the heart of our solar system, spiraling outward through worlds of fire, stone, ice and gas, until we drift beyond the familiar and into the eternal night between stars. Mercury, the innermost sentinel of our Sun, spins through its orbit in a peculiar dance that ancient astronomers could never have imagined, completing 3 rotations on its axis for every 2 journeys around our star. A gravitational waltz that means a single day-night cycle on this scorched world stretches across 176 Earth days, during which the Sun rises, sets, rises again in places, and traces bizarre loops across a black sky that never knows the softening haze of atmosphere. The surface of this small, dense world tells a story written in violence and silence, crater upon crater, overlapping like the rings left by raindrops in still water. Except these impacts occurred over billions of years, and the silence that followed each catastrophic collision has never been broken by wind, by water, or by any whisper of erosion. The Caloris Basin, a wound nearly 1,500 kilometers across, speaks of an impact so ferocious that shockwaves traveled through the entire planet and created a region of chaotic, jumbled terrain on the opposite side of the world. A testament to the raw energy that shaped these early solar system bodies when debris still rained from the primordial disk. The temperature on Mercury swings through extremes that would shatter any earthbound material, climbing to 430 degrees Celsius, where the Sun beats down upon its grey ancient face, then plummeting to nearly negative 180 degrees in the eternal shadows of deep craters near the poles, where ice clings to darkness despite this world's proximity to our blazing star. This ice, discovered by radar observations and confirmed by spacecraft, represents one of the solar system's most counterintuitive truths: that even on a world so close to the Sun, permanent shadow creates vaults cold enough to preserve water for billions of years. Mercury possesses the most eccentric orbit of any planet remaining in our solar system, swinging from 46 million kilometers at its closest approach to 70 million kilometers at its farthest. A variation so substantial that the Sun appears to change size dramatically when viewed from its barren plains. As we drift outward from this swift messenger world, we encounter Venus, shrouded in perpetual cloud cover so thick and so reflective that it blazes as the brightest object in our sky after the Sun and Moon. A beacon that ancient civilizations associated with love and beauty, never suspecting the hellscape that lurked beneath those pearlescent veils. The atmosphere of Venus weighs upon its surface with a pressure 92 times that of Earth, the equivalent of being submerged nearly a kilometer beneath our own oceans. And this crushing envelope of carbon dioxide has created a runaway greenhouse effect that makes Venus the hottest planet in our solar system, despite its greater distance from the Sun than Mercury. Surface temperatures on Venus hover around 465 degrees Celsius, hot enough to melt lead, hot enough to glow faintly in the darkness with the dull red radiance of heated rock. A world where even the mountains seem to sweat. The clouds of Venus consist not of water vapor but of sulfuric acid, drifting in 3 distinct layers between 48 and 70 kilometers above the surface. And within these corrosive mists, droplets form and fall as rain, evaporating long before they reach the scorched ground below in a cycle of chemical violence that never touches the planet's face. Venus rotates backward compared to most planets in our solar system, spinning from east to west so slowly that its day exceeds its year, taking 243 Earth days to complete a single rotation, while orbiting the Sun in only 225 days. A peculiar temporal arrangement that suggests some ancient catastrophe may have flipped this world upside down. The surface of Venus, mapped through its clouds by radar from orbiting spacecraft, reveals a landscape dominated by vast volcanic plains. Towering shield volcanoes like Mons rising 9 kilometers above the mean elevation, and strange circular features called coronae that may represent places where plumes of hot material rose from the mantle and reshaped the crust from below. Leaving Venus and its sulphurous beauty behind, we arrive at our own Earth, that pale blue dot suspended in the cosmic void, where liquid water flows across 71% of the surface, and life has transformed the very atmosphere into something unique among all the worlds we have yet discovered. The Earth's magnetic field, generated by the churning motion of molten iron in its outer core, extends thousands of kilometers into space and deflects the constant stream of charged particles flowing from the Sun, creating an invisible shield without which our atmosphere would have been stripped away billions of years ago, leaving us as barren as Mars. Our planet's axial tilt of 23.5 degrees gives us our seasons, a gentle wobble that means different hemispheres lean toward or away from the Sun as we orbit, creating the eternal cycle of spring, summer, autumn and winter that have shaped the evolution of countless species. The Moon that accompanies Earth through space is unusually large compared to its parent planet, a quarter of Earth's diameter and sufficient in mass to make our world wobble slightly as the two bodies dance around their common center of gravity, which lies not at Earth's core, but rather about 1,700 kilometers below its surface. This lunar companion stabilizes Earth's axial tilt, preventing the wild oscillations that would otherwise occur over millions of years, and that would have made our climate so chaotic that complex life might never have evolved. A quiet gift from our silver satellite that goes largely unappreciated. The Earth-Moon system likely formed from violence, from a collision between the young Earth and a Mars-sized body called Theia, approximately 4.5 billion years ago. An impact that liquefied much of our planet and flung debris into orbit that gradually coalesced into the Moon we see tonight. Drifting further from the Sun, we encounter Mars, the rust-colored world that has captured human imagination for centuries, whose color comes from iron oxide coating its surface, the same compound that turns blood red and gives autumn leaves their final blush before falling. Mars possesses the largest volcano in the solar system, Olympus Mons, which rises 22 kilometers above the surrounding plains, nearly 3 times the height of Mount Everest. A shield volcano so broad that its base would cover most of France, and so gently sloped that standing at its summit, one would not be able to see its edges disappear over the curved horizon. The caldera atop this titanic mountain contains multiple collapse craters, testament to the countless eruptions that built this edifice over hundreds of millions of years, during an era when Mars was geologically active and perhaps even hosted liquid water on its surface. Valles Marineris stretches across the face of Mars like a scar from some unimaginable wound, a canyon system 4,000 kilometers long, 200 kilometers wide, and up to 7 kilometers deep, dwarfing Earth's Grand Canyon as a cathedral dwarfs a closet. This vast chasm may have formed as a Tharsis volcanic region bulged upward billions of years ago, cracking the crust like an eggshell, and creating rift valleys that subsequent water erosion may have deepened and widened into the labyrinth we see today. Mars today possesses only a thin atmosphere, less than 1% of Earth's surface pressure, composed almost entirely of carbon dioxide, with traces of nitrogen and argon. Too thin to support liquid water on the surface, but thick enough to create dust storms that can engulf the entire planet for months at a time. Evidence written in the Martian landscape suggests that rivers once flowed across this now desiccated world, carving channels and depositing sediments in patterns that mirror those left by water on Earth, pointing to an ancient era when Mars may have been warm and wet, perhaps even harbouring conditions suitable for life. The polar ice caps of Mars contain vast quantities of water ice and frozen carbon dioxide, expanding and contracting with the Martian seasons, and beneath the southern cap lies what some scientists believe may be a subterranean lake of liquid water, kept from freezing by the pressure of kilometers of ice above and by salts that lower the freezing point. Mars possesses two small, irregularly shaped moons, Phobos and Deimos, captured asteroids that tumble through Martian skies, with Phobos orbiting so close and so fast that it rises in the west and sets in the east, crossing the sky in just 4 hours and appearing to move backward against the stars. As we leave the realm of the rocky inner planets and cross the asteroid belt, that diffuse ring of primordial rubble that never quite coalesced into a planet due to Jupiter's gravitational interference, we approach the gas giants, worlds of such different character that they seem to belong to another solar system entirely. Jupiter, king of the planets, contains more mass than all other planets combined, multiplied by 2.5. A world so large that 1,300 Earths could fit within its volume, yet composed almost entirely of hydrogen and helium, the same elements that fuel the Sun itself. The atmosphere of Jupiter displays a mesmerizing pattern of colored bands, zones of rising bright ammonia, clouds alternating with belts of sinking darker material, driven by the planet's rapid rotation that completes a day in just under 10 hours, despite Jupiter being 11 times Earth's diameter. The Great Red Spot has raged on Jupiter for at least 350 years, a storm so vast that Earth could fit within it with room to spare. An anticyclonic vortex that rotates counterclockwise every 6 Earth days and towers 8 kilometers above the surrounding cloud tops, though recent observations suggest this iconic feature may be shrinking over time. Jupiter possesses no solid surface in any meaningful sense, merely an atmosphere that grows denser and hotter as one descends, transitioning gradually from gas to supercritical fluid to a state of matter unlike anything on Earth, where hydrogen is compressed so intensely that it becomes metallic, conducting electricity and generating the most powerful magnetic field of any planet in our system. The magnetosphere of Jupiter extends millions of kilometers into space, trapping charged particles in radiation belts so intense that they would kill an unshielded human in minutes, creating an invisible but deadly barrier around this giant world. Jupiter's family of moons numbers at least 95 confirmed members, but 4 of these stand out as worlds unto themselves, discovered by Galileo in 1610, and forever changing our understanding of our place in the cosmos by demonstrating that not everything orbits the Earth. Io, the innermost of these Galilean moons, experiences gravitational forces from Jupiter and the other large moons that flex and heat its interior, creating the most volcanically active body in the solar system, its surface constantly reshaped by eruptions of sulfur and silicate lava that paint it in yellows, oranges, reds and blacks like a diseased orange left too long in the sun. Europa, slightly smaller than Earth's moon, hides beneath a shell of water ice that appears smooth and young on a cosmic scale, crisscrossed with reddish-brown fractures where something from below has welled up and frozen. And beneath that ice lies a global ocean of liquid water that contains perhaps 2 to 3 times as much water as all of Earth's oceans combined. The ice shell of Europa may be only a few kilometers thick in some places, thin enough that tidal flexing creates fresh cracks, and perhaps even allows plumes of ocean water to spray into space, where spacecraft might someday fly through them and taste what swims below, without ever having to drill through the frozen crust. Ganymede, the largest moon in the solar system, exceeds even the planet Mercury in diameter, possessing its own magnetic field generated by a liquid iron core. A world of mixed ice and rock, whose surface tells stories of ancient geological activity, now long quiet. Callisto, the outermost of the four, bears the most heavily cratered surface in the solar system, a face unchanged for 4 billion years, so ancient that it serves as a record of the bombardment that pummeled all worlds during the solar system's violent youth. Beyond Jupiter, we encounter Saturn, that breathtaking vision of celestial architecture, whose ring system spans nearly 300,000 kilometers, from inner to outer edge, yet averages only 10 meters in thickness, proportionally thinner than a sheet of paper scaled to the size of a football field. The rings of Saturn consist of billions upon billions of particles, from grains smaller than sand to boulders the size of houses, each composed primarily of water ice with traces of rocky material, each orbiting independently in a flattened disk that catches and scatters sunlight into subtle colors. The main rings are divided into named sections, separated by gaps, the most prominent being the Cassini division, a dark lane 4,800 kilometers wide, created by the gravitational influence of the Moon. Mimas, which orbits at a period precisely twice that of particles in the gap, repeatedly tugging them into different orbits. Saturn itself is the least dense planet in our solar system, so buoyant that if one could find an ocean large enough, Saturn would float upon its waters. A world where hydrogen and helium dominate an atmosphere banded with more subtle colors than Jupiter's, pale yellows and ochres that speak of similar chemistry but colder temperatures at this greater distance from the Sun. Wind speeds on Saturn can exceed 1,800 kilometers per hour at the equator, creating jet streams that dwarf any atmospheric phenomena on Earth. While at the North Pole, a persistent hexagonal storm pattern spans 29,000 kilometers, a geometric anomaly that has puzzled scientists since its discovery, and demonstrates the strange beauty that emerges from fluid dynamics at planetary scales. Titan, Saturn's largest moon, stands alone in the outer solar system as the only moon with a dense atmosphere. An orange haze of nitrogen and organic compounds that hides its surface from visible light and gives it an appearance something like a smog-choked city viewed from above. The surface of Titan, revealed by radar and infrared observations and by the Huygens lander that descended through its skies in 2005, features lakes and seas of liquid methane and ethane. Black mirrors that reflect the dim sunlight filtered through kilometers of hydrocarbon haze, the only stable bodies of surface liquid known anywhere beyond Earth. Rain falls on Titan, but it is not water that descends from those orange clouds, rather liquid methane that carves channels and fills basins, creating a hydrological cycle achingly familiar in its patterns, yet utterly alien in its chemistry. Enceladus, a small moon only 500 kilometers across, harbors a secret beneath its icy surface that makes it one of the most intriguing destinations in our solar system. For through fissures near its south pole, jets of water vapor and ice crystals spray hundreds of kilometers into space, revealing an ocean of liquid water maintained by tidal heating. The material erupting from Enceladus contains not only water, but organic molecules, silica particles that suggest hydrothermal activity on the ocean floor, and salts that indicate the water has been in contact with rock, all ingredients that on Earth are associated with the origin and sustenance of life. Saturn possesses numerous other moons, each with its own character, from Mimas with its enormous crater that makes it resemble the Death Star, to Iapetus with its two-toned surface, one hemisphere dark as coal and the other bright as snow. A mystery that may involve material swept up from outer moons, or from processes we do not yet understand. As we continue outward into the colder, darker reaches of our solar system, we encounter Uranus, the first planet discovered in the modern era, a pale blue-green sphere that William Herschel initially mistook for a comet in 1781, before its true nature became clear through careful observation of its orbit. Uranus is tilted on its side. Its rotational axis inclined 98 degrees from perpendicular to its orbital plane. So extreme that the planet essentially rolls around the Sun rather than spinning upright, likely the result of a collision with an Earth-sized object early in solar system history that knocked this giant world onto its side. This extreme tilt means that seasons on Uranus last 21 Earth years each, and that during solstices, one pole faces the Sun continuously, while the other remains in perpetual darkness, a pattern of light and shadow unlike any other major planet. The atmosphere of Uranus contains methane that absorbs red wavelengths of light and scatters blue and green back to observers, giving this world its distinctive cyan color, a subtle shade that speaks of cold chemistry far from solar warmth, where temperatures in the upper cloud layers drop to negative 224 degrees Celsius. Unlike Jupiter and Saturn, Uranus radiates almost no more heat than it receives from the Sun, suggesting that whatever warmth remained from its formation has long since dissipated, or that some insulating layer traps heat deep within and prevents its escape to space. Another mystery surrounding this enigmatic ice giant. The ring system of Uranus, discovered only in 1977, is narrow, dark, and composed of particles so much smaller and less reflective than Saturn's rings that they remained invisible for centuries despite telescopic observation, a subtle adornment around a subtle world. Neptune, the outermost of the major planets, was discovered through mathematics, before anyone saw it through a telescope. Its existence predicted from perturbations in the orbit of Uranus that could only be explained by the gravitational pull of an unseen world lurking in the darkness beyond. This deep blue planet, colored by methane in a similar manner to Uranus, but displaying a more vivid azure due to other compounds not yet fully identified, hosts the fastest winds in the solar system, screaming at speeds up to 2,100 kilometers per hour, despite receiving so little energy from the distant Sun. The Great Dark Spot, observed by Voyager 2 in 1989, was an anticyclonic storm, similar in some ways to Jupiter's Great Red Spot. But unlike that enduring feature, Neptune's storm had vanished by the time the Hubble Space Telescope observed the planet a few years later, replaced by new storms in different locations. A reminder that even on worlds where everything seems frozen and eternal, change still occurs. Triton, Neptune's largest moon, is almost certainly a captured Kuiper belt object, dragged into orbit around Neptune by some ancient gravitational encounter. For it orbits in the wrong direction, retrograde to the planet's rotation, a configuration impossible for a moon that formed from the same disk of material as its parent planet. The surface of Triton is among the coldest in the solar system, averaging -235 degrees Celsius, a world where nitrogen freezes solid and geysers of nitrogen gas erupting through the ice paint. Dark streaks across the pinkish terrain. Triton's retrograde orbit means that tidal forces are gradually slowing the moon and causing it to spiral inward. And in perhaps 1 billion years, this captive world will cross within Neptune's Roche limit and be torn apart by gravitational forces, perhaps forming a ring system that would rival Saturn's for a cosmic instant before dispersing. Beyond Neptune lies the Kuiper belt, a region of space extending from roughly 30 to 50 astronomical units from the Sun, populated by icy bodies left over from the formation of the solar system, a frozen reservoir of primordial material that has remained largely unchanged for 4.5 billion years. Pluto, once classified as the 9th planet, now stands as the most famous resident of this distant realm, a world only 2/3 the diameter of Earth's moon, but possessed of 5 moons of its own, the largest of which, Charon, is so large relative to Pluto that the two orbit each other around a point in empty space between them. A true binary dwarf planet system. The New Horizons spacecraft revealed Pluto to be far more geologically complex than anyone expected, with mountains of water ice rising 3 kilometers above frozen nitrogen plains, and a heart-shaped region called Sputnik Planitia, that appears to be a vast glacier of nitrogen ice, slowly convecting in cellular patterns like simmering water in a pot. The atmosphere of Pluto is thin, less than 100,000th of Earth's surface pressure, but it extends surprisingly high above the surface and creates multiple layers of haze that scatter blue light and paint this distant world with an azure glow against the blackness of space when viewed from behind. Pluto's surface displays a remarkable variety of terrains and colors, from bright nitrogen ice to dark reddish-brown organic compounds called tholins, created when ultraviolet light and cosmic rays break apart methane molecules in the atmosphere, and the fragments recombine into complex organic compounds that drift down and coat the surface. The Kuiper belt contains perhaps hundreds of thousands of objects larger than 100 kilometers across, and millions more of smaller size. A vast ring of frozen relics that extends outward and eventually merges into the even more distant Oort cloud. Eris, discovered in 2005, is slightly smaller than Pluto, but more massive, composed of rock and ice in proportions that suggest a higher density than its inner neighbour, orbiting at distances that range from 38 to 97 astronomical units from the Sun in an orbit tilted 44 degrees from the main plane of the solar system. Makemake, Haumea, and other dwarf planets populate this realm, each with their own peculiarities. Haumea spinning so rapidly that it has been elongated into an egg shape and possesses a thin ring of its own, the first such feature discovered around a trans-Neptunian object. These distant worlds receive so little sunlight that at noon on their surfaces the illumination is dimmer than a moonlit night on Earth, and the Sun itself appears merely as an extraordinarily bright star. No longer the blazing disk that dominates inner system skies. The scattered disk extends beyond the classical Kuiper belt, a region of space where gravitational perturbations from Neptune have flung objects into highly elliptical orbits that can carry them out to hundreds of astronomical units from the Sun before swinging them back in again. A population of cosmic wanderers tracing enormous loops through the darkness. Sedna, one of the most distant objects yet discovered in our solar system, never approaches closer than 76 astronomical units from the Sun, even at perihelion, and swings out to over 900 astronomical units at aphelion. An orbit so vast that it takes over 11,000 years to complete, raising questions about what gravitational influence shaped such an extreme path. Some astronomers have proposed that the orbits of Sedna and similar objects suggest the presence of an as yet undiscovered massive planet, sometimes called Planet 9, lurking in the outer reaches of our solar system, its gravitational influence shepherding distant objects into their current configurations. Though this hypothetical world remains undetected despite extensive searches. Far beyond even these scattered objects lies the Oort cloud, a spherical shell of icy bodies extending perhaps 100,000 astronomical units from the Sun, nearly halfway to the nearest star. A repository of trillions of comets that occasionally fall inward to grace our skies with their glowing tails. The Oort cloud is theoretical, in the sense that we have never directly observed its distant members, but its existence is inferred from the long-period comets that occasionally appear in the inner solar system, arriving from all directions rather than from the disc-shaped regions of the Kuiper belt, their orbits testifying to a source population distributed in a vast sphere. The boundary between our solar system and interstellar space is not marked by any physical barrier, but rather by the heliopause, where the outward pressure of the solar wind finally balances the inward pressure of the interstellar medium, a transition zone that the Voyager spacecraft have now crossed, becoming humanity's first emissaries to the space between stars. Leaving our solar system behind and drifting into the void between stars, we find ourselves in the interstellar medium, a space that seems empty, but is populated by roughly 1 atom per cubic centimetre. Hydrogen and helium, left over from the Big Bang, along with heavier elements forged in the hearts of long-dead stars. This tenuous gas is not uniformly distributed, but rather clumped into clouds of varying density, some so diffuse that light travels through them unimpeded, others dense enough to block the light of background stars and appear as dark nebulae against the glow of the Milky Way. The interstellar medium is threaded with magnetic fields and cosmic rays, high-energy particles accelerated to nearly the speed of light by supernovae and other violent events. A radiation environment that any future spacecraft traversing these distances would need to withstand. The nearest star system to our own is Alpha Centauri, a triple star system located about 4 1/3 light-years away, meaning that light leaving those stars tonight will not reach us until well into the next decade, a distance so vast that our fastest spacecraft would take tens of thousands of years to traverse it. Alpha Centauri A and B are a binary pair orbiting each other every 80 years, both similar to our Sun in size and temperature, while Proxima Centauri is a small red dwarf orbiting the main pair at a distance so great that it takes over 500,000 years to complete one orbit. Proxima Centauri has been confirmed to host at least one planet in its habitable zone, Proxima Centauri b, a world about the same mass as Earth, that receives a similar amount of energy from its star as we receive from ours. Though whether this world could support life remains uncertain given the violent flares that red dwarfs produce. Red dwarfs like Proxima Centauri are the most common type of star in the galaxy, comprising roughly 75% of all stars, small, cool, and so frugal with their nuclear fuel that they can burn for trillions of years, far longer than the current age of the universe. These dim stellar embers are so faint that not a single red dwarf is visible to the naked eye from Earth, despite their overwhelming numbers, each one a small furnace of hydrogen fusion that could host planetary systems we have yet to detect. Planets around red dwarfs face challenges that Earth does not, including tidal locking that would cause one side to perpetually face the star while the other remains in eternal darkness, and intense stellar flares that could strip away atmospheres and irradiate surfaces. Yet despite these obstacles, the sheer number of such stars makes them prime targets in the search for habitable worlds. Beyond the Alpha Centauri system, stars are scattered through the galaxy at average distances of several light-years from one another, though in some regions they cluster much more densely, and in others they are separated by vast gulfs of emptiness. Barnard's star, the second closest stellar system to our Sun at about 6 light-years, is another red dwarf moving through space faster than any other star relative to our Sun, covering the width of the full moon against the background stars every 180 years. Barnard's star was once thought to host planets based on apparent wobbles in its motion, a claim later discredited, though recent observations suggest at least one planet may exist there after all. The history of this system reminding us how difficult it is to detect worlds around other stars. The stars, visible to our naked eyes on a clear night number only a few thousand, representing merely the nearest and brightest members of a galaxy that contains between 100 billion and 400 billion stars. A number so large that if you counted one star per second, it would take you thousands of years to count them all. The Milky Way galaxy stretches roughly 100,000 light-years across, a flattened disk of stars, gas and dust, with a central bulge and spiral arms where star formation occurs most actively, all of it rotating around a common center that takes our solar system about 230 million years to orbit once. At the heart of our galaxy lurks a supermassive black hole, Sagittarius, a star, with a mass 4 million times that of our Sun, a gravitational monster around which stars whirl at thousands of kilometers per second, occasionally being torn apart when they venture too close. Spiral galaxies like our own are cosmic pinwheels of tremendous beauty, their arms traced out by young blue stars, and the pink nebulae where those stars form. Winding patterns that arise from density waves propagating through the galactic disk, compressing gas and triggering star birth in a slow-motion pattern that takes hundreds of millions of years to complete one revolution. The spaces between spiral arms are not empty, but simply contain fewer of the bright young stars that make the arms visible. Older yellow and red stars populating these regions in numbers that would still seem vast by any human standard. Our solar system currently resides in a minor spur between two major spiral arms, the local arm, or Orion spur, a relatively quiet neighborhood that has allowed life to develop on Earth without the catastrophic disturbances that might occur closer to regions of active star formation. Elliptical galaxies present a different aspect entirely. Smooth, ellipsoidal collections of stars that range from nearly spherical to highly elongated. Lacking the organized spiral structure of galaxies like the Milky Way, their stars orbiting the galactic center in random orientations rather than a coherent disk. These galaxies are often ancient, their star formation having largely ceased billions of years ago, leaving populations of old red and orange stars that glow with a warm but fading light. Stellar cities whose busiest days are long past. The largest galaxies in the universe are giant ellipticals found at the centers of galaxy clusters, containing up to 100 trillion stars, formed through the mergers of smaller galaxies over cosmic time. Irregular galaxies possess neither spiral arms nor elliptical shapes, their structures disrupted by gravitational interactions with neighboring galaxies, or perhaps simply never having settled into orderly forms. Chaotic collections of stars and gas that nonetheless host vibrant star formation in their tumultuous interiors. The large and small Magellanic Clouds, visible to observers in the southern hemisphere as detached patches of the Milky Way, are irregular dwarf galaxies orbiting our own, their gravitational interaction with the Milky Way drawing out streams of gas that may eventually fuel new star formation in our galaxy. These companion galaxies have been falling toward the Milky Way for billions of years and will eventually merge with it entirely, their stars scattered and absorbed into our galactic disk. Galaxies are not randomly distributed through the universe, but rather organized into structures of increasing scale. From small groups like our own local group containing a few dozen galaxies, to massive clusters containing thousands of galaxies bound together by gravity. The Virgo cluster, the nearest large cluster to our local group, contains over 1,000 galaxies, spanning a region more than 15 million light-years across, and its combined gravitational pull is slowly drawing the local group toward it through the expansion of space. Galaxy clusters are themselves organized into superclusters, filaments, and walls that form a cosmic web when viewed at the largest scales, a foam-like structure where galaxies trace out the boundaries of vast voids containing almost nothing at all. The Laniakea supercluster, our home supercluster, spans over 500 million light-years and contains the mass of 100 million billion suns, a gravitational basin within which all motion flows toward an enigmatic concentration of mass called the Great Attractor. This structure was only mapped in detail in 2014, revealing for the first time the full extent of the cosmic watershed within which our galaxy resides, a discovery that placed our address in the universe in its proper context. The Great Attractor itself lies hidden behind the dust and stars of our own galactic plane, in a region of sky called the Zone of Avoidance, where our view of the extragalactic universe is blocked by intervening material. Between the galaxies and clusters lies the intergalactic medium, an even more tenuous sea of gas than the interstellar medium, heated to millions of degrees in some regions by the shock waves from colliding galaxy clusters and the outflows from supermassive black holes. This hot gas is nearly invisible at optical wavelengths, but glows brightly in X-rays, revealing vast clouds and filaments that trace the scaffolding of the cosmic web, the baryonic matter that accompanies the dark matter halos within which galaxies form. Most of the ordinary matter in the universe exists in this form, not in stars or planets, but in the diffuse, superheated gas that fills the spaces between galaxies, a hidden reservoir that remained undetected until X-ray telescopes opened this window on the cosmos. Exoplanets, worlds orbiting stars other than our Sun, were once mere speculation, but are now known by the thousands, each detection revealing another solar system with its own architecture, its own history, and its own potential for conditions that might, or might not support life. The first exoplanet orbiting a Sun-like star was discovered in 1995, a gas giant whirling around its star in just 4 days at a distance, so close that its surface would glow with the heat of its proximity. A type of world unknown in our solar system and dubbed a hot Jupiter. Since then, the catalogue has expanded to include over 5,000 confirmed planets, and many more candidates awaiting verification. A population that suggests planets are the rule rather than the exception around stars. Hot Jupiters remain among the easiest exoplanets to detect because their size and proximity to their stars create observable effects. But they represent only a tiny fraction of the true planetary population, their discovery biased by the methods we use rather than reflecting reality. The transit method, which detects planets by the slight dimming of a star's light when a planet passes in front of it as seen from Earth, has been particularly fruitful, with the Kepler Space Telescope alone discovering thousands of candidates before its mission ended. The radial velocity method, which detects the tiny wobble a planet's gravity induces in its host star, confirmed many of these discoveries and remains a powerful complementary technique. Super-Earths, planets with masses between Earth's and Neptune's, appear to be extraordinarily common in other solar systems, a class of world entirely absent from our own system, raising questions about why our planetary neighbourhood developed differently from so many others. These worlds might have thick atmospheres of hydrogen and helium, like smaller versions of Neptune, or they might be rocky worlds scaled up from Earth, their compositions and conditions varying enormously depending on where and how they formed. The line between large rocky planets and small gaseous planets remains uncertain, and determining the true nature of individual super-Earths requires detailed observations that push the limits of current technology. Some exoplanets orbit within the habitable zones of their stars, those regions where temperatures might allow liquid water to exist on a planetary surface given the right atmospheric conditions, a criterion often used as a first approximation of potential habitability. The habitable zone varies enormously depending on the star, lying much closer in for dim red dwarfs than for bright sun-like stars. And the question of whether a planet in the habitable zone is actually habitable depends on countless factors we cannot yet determine from our distant vantage point. Venus lies at the inner edge of our Sun's habitable zone, and Mars at the outer edge. Yet neither world supports life today. A reminder that location alone does not determine habitability. The TRAPPIST-1 system, discovered in 2016, characterized in detail since, contains 7 rocky planets orbiting a small red dwarf star just 40 light-years away, with several of these worlds receiving similar amounts of energy from their star, as Earth receives from the Sun. These planets are so close together that from the surface of one, the others would appear as large as or larger than our Moon in Earth's sky, a truly alien vista of sister worlds hanging in an orange-tinted sky beneath a dim stellar ember. The TRAPPIST-1 system has become a primary target for atmospheric characterization by the James Webb Space Telescope, which may be able to detect the presence or absence of atmospheres on these worlds, and perhaps even identify specific gases that could hint at geological or biological activity. Rogue planets wander through the galaxy unbound to any star, ejected from their parent systems by gravitational interactions with other planets or stars, drifting through interstellar space in eternal darkness, with no sun to warm them. These wandering worlds may be extraordinarily common, perhaps outnumbering stars in the galaxy, though they are extremely difficult to detect since they emit no light of their own and reflect none from absent parent stars. Some rogue planets may retain internal heat from radioactive decay or primordial formation energy, and if they possess thick hydrogen atmospheres, this internal warmth might even maintain liquid water beneath icy shells, a strange but possible habitat for life far from any stellar hearth. Pulsar planets orbit the rapidly spinning remnants of exploded stars. Neutron stars that beam radio waves like cosmic lighthouses, and are called pulsars because of this pulsating emission pattern as seen from Earth. The first confirmed exoplanets were actually discovered around a pulsar in 1992. Their existence inferred from subtle variations in the timing of the pulsar's radio pulses, as the gravity of orbiting worlds tugged the neutron star back and forth. These worlds likely formed from the debris of the supernova that created the pulsar, or from material captured from a companion star, inhospitable places bathed in intense radiation, yet representing the first concrete evidence that planets exist beyond our solar system. Brown dwarfs occupy a twilight realm between the smallest stars and the largest planets, objects massive enough to fuse deuterium in their cores, but not massive enough to sustain the hydrogen fusion that powers true stars, slowly cooling over billions of years as their initial heat radiates away. These failed stars glow dimly in infrared wavelengths, their temperatures and brightnesses declining throughout their existence, and some brown dwarfs have been found to host planetary systems of their own. The boundary between the largest planets and the smallest brown dwarfs remains somewhat arbitrary, defined by the deuterium fusion limit at roughly 13 Jupiter masses, though the objects themselves show no discontinuity in properties at this threshold. Binary and multiple star systems are common throughout the galaxy, and planets in these systems face complex gravitational environments that can create exotic orbital configurations unknown in our relatively simple single-star system. Circumbinary planets orbit both stars of a binary pair, their nights illuminated by two suns and their years defined by the orbit around the stellar center of mass rather than around either star individually. Planets orbiting just one star of a binary pair experience periodic gravitational perturbations when the companion star approaches, potentially causing climate variations and orbital changes over millions of years. The atmospheres of exoplanets have begun to yield their secrets to spectroscopic analysis, with observations detecting water vapor, carbon dioxide, methane, and other molecules in the extended upper atmospheres of hot Jupiters and other large worlds. These measurements rely on observing starlight filtered through a planet's atmosphere during transit, with specific wavelengths absorbed by specific molecules, creating a chemical fingerprint that reveals atmospheric composition. Extending these techniques to smaller, cooler, potentially habitable worlds remains a tremendous challenge, requiring larger telescopes and more precise measurements. But the field advances steadily toward this goal. Planetary formation remains an active area of research, with observations of protoplanetary disks around young stars revealing the birthplaces of planets in unprecedented detail, rings and gaps and spirals that trace the gravitational influence of unseen worlds still in the process of formation. The ALMA radio telescope array has been particularly powerful in this regard, mapping the distribution of dust and gas around stars ranging from mere hundreds of thousands to several million years old, catching planetary systems at various stages of their development. These observations have revealed that many features once thought to indicate planets, such as gaps in protoplanetary disks, can also arise from other processes, requiring careful analysis to distinguish forming planets from alternative explanations. The fates of planetary systems are tied to the fates of their stars, and as stars evolve, the conditions in their systems change dramatically, potentially rendering once habitable worlds uninhabitable or transforming frozen worlds into briefly clement ones. When sun-like stars exhaust their hydrogen fuel and expand into red giants, they engulf their inner planets and blast their outer planets with intense radiation and stellar winds, destroying any life that might have existed and fundamentally altering planetary surfaces and atmospheres. White dwarfs, the stellar remnants left after red giant evolution, have been found to possess debris disks and even small planets, either surviving remnants from before the star's evolution or newly formed from disrupted asteroids and former planets. The search for extraterrestrial intelligence continues against this backdrop of planetary discovery, informed by the growing realization that planets are common, that habitable zone worlds exist in large numbers, and that the conditions for life as we understand it may arise frequently throughout the cosmos. Radio telescopes listen for signals from technological civilizations, searching for patterns that cannot be explained by natural phenomena, while optical telescopes look for laser pulses or other signatures of advanced engineering. No confirmed signals have been detected despite decades of searching. A silence that could mean civilizations are rare, that they are short-lived, that they do not produce detectable signals, or simply that we have not yet searched enough of the vast cosmic haystack. The scale of the observable universe extends far beyond our galaxy, encompassing hundreds of billions of galaxies, each containing billions of stars. A volume of space roughly 92 billion light-years in diameter, created not by expansion of galaxies through space, but by the expansion of space itself, carrying galaxies apart. Looking to great distances means looking back in time, since light from distant objects has taken billions of years to reach us, and the most distant galaxies we observe are seen as they existed when the universe was young. Their light redshifted by the expansion of space until optical light has shifted into infrared wavelengths. The cosmic microwave background radiation, the afterglow of the Big Bang itself, represents the most distant thing we can observe. Light released when the universe was just 380,000 years old, and the primordial plasma cooled enough for atoms to form and space to become transparent. Dark matter, detected only through its gravitational effects, appears to outweigh ordinary matter in the universe by roughly 5 to 1, providing the gravitational scaffolding within which galaxies form and cluster, yet remaining utterly mysterious in its fundamental nature despite decades of investigation. This invisible mass does not interact with light, does not clump into stars or planets, and passes through ordinary matter like a ghost. Yet without it, galaxies would fly apart, and the universe would never have developed the structures we observe today. Candidates for dark matter particles range from weakly interacting massive particles to axions to primordial black holes. But experiments designed to detect these candidates have so far returned only null results, deepening the mystery. Dark energy, even more mysterious than dark matter, appears to compose roughly 68% of the total energy content of the universe, driving the acceleration of cosmic expansion that was discovered in 1998 through observations of distant supernovae. This repulsive force overwhelms gravity at the largest scales, causing the universe to expand faster and faster rather than slowing down, as would be expected from matter and radiation alone, and its nature remains completely unknown. Some physicists suggest that dark energy is simply the inherent energy of empty space, a cosmological constant in the equations of general relativity, while others propose that it is a dynamic field that changes over time, with profound implications for the ultimate fate of the cosmos. The future of the universe stretches ahead for timescales that dwarf human comprehension, eras when the familiar stars will have long since burned out, and only the slow decay of matter and black holes will mark the passage of time in an ever-cooling, ever-expanding cosmos. In roughly 5 billion years, our Sun will exhaust its hydrogen fuel and swell into a red giant. But this stellar death is merely a local event against the eternal backdrop of cosmic evolution. Over trillions of years, star formation will gradually cease as the raw material for new stars is consumed or locked away in stellar remnants, and the lights in the universe will slowly wink out. The longest-lived stars, the smallest red dwarfs, may continue to shine for perhaps 10 trillion years. But eventually, even these will exhaust their fuel and fade into white dwarfs, then cool over quadrillions of years into black dwarfs, stellar corpses emitting no light whatsoever. Black holes will eventually dominate the universe, and even these will slowly evaporate through Hawking radiation, a quantum mechanical process that predicts the eventual demise of all black holes over timescales of 10 to the power of 100 years and beyond. In the final era, if our current understanding is correct, the universe will consist of nothing but scattered particles drifting through an ever-expanding void, the temperature approaching but never quite reaching absolute zero, a state of maximum entropy and minimum structure. Yet, against this backdrop of cosmic endings, the present moment shines with possibility. A brief era when stars still burn, when planets still form, when life still exists to contemplate the darkness between the worlds and wonder at the strange beauty of it all. Every atom in your body was forged in the heart of a star that died billions of years ago, scattered into space by supernova explosion, gathered into a new solar system, incorporated into a planet, and eventually assembled into the intricate architecture of life. You are the universe contemplating itself, stardust become conscious, a temporary arrangement of matter and energy that can look up at the night sky and feel connected to everything that has ever existed or will ever exist. Let this knowledge settle over you like a blanket of stars. Let the immensity of space and time quiet the concerns of the day, and drift now towards sleep, knowing that you are part of something vast and ancient and ongoing, a story that began before the Earth was formed and will continue long after everything we know has transformed into something new. The planets spin in their orbits, the stars burn in their furnaces, the galaxies wheel through the void, and somewhere in all that darkness and distance, on a small blue world circling an ordinary yellow star, you close your eyes and rest. One small but essential part of the cosmic whole, exactly where you belong in this moment, at peace with the infinite.